So good afternoon, everyone. Can we please be seated? There are a few chairs sprinkled, empty chairs sprinkled up here, a few over here. You'll have to come down front. We can't have you sitting in the aisles due to fire codes, so if you're saving seats for someone, we'll have to go ahead and forego that. And we're going to go ahead and get started. So everyone, welcome to our second Green Talk of Fall 17. We have with us today Forrest Melton. He is a senior research scientist with NASA, as well as Cal State University, Monterey Bay. Went to undergrad at Stanford University, and I'm going to allow him to tell you the rest of his background. My name is Barbara Murphy-Wesley. I am a fellow 100W teacher, and I'd like to welcome everybody. Let's give Dr. Melton a warm welcome.
Thank you so much. Nice to see all of you. I work over at NASA Ames Research Center, also as a research scientist at Cal State Monterey Bay. Before I get started, I don't want to forget this. If you're interested in working with NASA, interested in internships, interested in remote sensing and earth science, be sure to Google NASA Develop. The NASA Develop program is an internship program, and we host anywhere between a dozen and about 20 students at Ames every summer. Fantastic program. So my day job is mostly comprised of using satellite data to understand changes on the Earth's surface. I do a lot of work on applications of satellite data to measure different hydrologic variables, and in particular to look at crop water requirements, crop water demands, and crop use in agriculture, as well as to monitor changes in agricultural production. I also spent about half my time over the last 4 or 5 years working on data sets for the National Climate Assessment, and contributed to an interagency working group that developed tools to try to improve public access to those data sets for folks exactly like you. Engineers, city planners, folks that are trying to come up with solutions to climate change to improve climate resiliency over the coming decades. Now, unfortunately, I didn't realize that Dr. Cordero also was going to talk to you about climate change last week. I hope I'm going to give you some slightly different graphics, different presentations. I'll touch on some of the same topics he touched on, but I hope to give you some additional perspectives on that. Two things. So the two most important things to take away from today. One, take a look at the U.S. Climate Explorer for the U.S. Climate Resilience Toolkit. This is a tool that has been developed by NOAA, NASA, the USGS, EPA, working with U.S. Global Change Research Program and the Bureau of Reclamation to try to increase and improve the ability to access these data sets in ways that are easy to understand and easy to create summaries for. Again, the primary goal is to inform planning and for resilience to climate change, but it's also a really useful way to get local scale information on future climate conditions and potential climate change impacts. So the URL is there. If you have a laptop, feel free to browse while I'm talking. I won't be offended. Take a look. The other key message is, as engineers, I hope you will read the National Climate Assessment. All right? As engineers, your job day to day will be to solve problems. This is a list of the problems that we will be facing. Right? So there are potential challenges for civil engineers, for electrical engineers, for biomedical engineers, for structural engineers. The whole, if you can think of a problem, it's probably going to intersect with climate change at some point in time. The third National Climate Assessment was published in 2014. I worked on some of the technical reports that served as the basis for the chapters on ecosystem services and biodiversity. The fourth National Climate Assessment is in progress, and the Special Climate Report is now available there on the NCA website. So be sure to come back at some point and take a look at some of these sites, browse through the materials, at least read the executive summaries for these reports. I think you'll find it well worth your time. And also, as a technical writing course, I think this is a great example of technical writing. Scientists, I can't tell you how many hours and hours we spend trying to get the phrasing right, reducing hundreds and hundreds of papers into the most important points and graphics. So this is a nice example of how teams of scientists work together to write. If you read it and you think it's unclear, let me know. If you think you can do better, I hope you'll have a chance to get involved in the future. But in terms of a technical document that's written for the public and tries to translate detailed scientific and technical information into understandable and usable formats and key bullet points, I think this is a really nice example. And again, we're well worth some time exploring what's available in the National Climate Assessment. So what I'd like to do today is talk a little bit about climate change causes, impacts, and solutions. And then I'm going to touch on just a few examples of how we produce data sets for the U.S. Climate Explorer and the National Climate Assessment. And then I'll touch on the U.S., I'll give you some examples and walk you through some of the features of the Climate Explorer itself. So first, causes. You guys have probably all seen a slide like this one here on the right in terms of the total U.S. greenhouse gas emissions by economic sector. I'm guessing Dr. Cordero showed you something like this. I think something we don't do well as humans is envision large numbers and their impacts, right? So each year we burn globally close to 33 billion barrels of oil, 8.6 billion tons of coal, and 120 trillion cubic feet of natural gas. Those are big numbers, right? It's hard to get your mind around them. As an engineer, when you encounter a big number, I would encourage you to translate the units. Convert it to something that's easy to visualize and gives you a sense of the number and the scale of the problem you're trying to deal with. So for oil, how many of you have driven from Bakersfield to Butte, up and down the Central Valley? Anyone? Or just driven across the Central Valley, going over to Yosemite or Sequoia or up to the Sierra at any point? Yeah. That's big, right? 22,500 square miles. If we took all the oil that we burn each year, you would cover that about ankle deep, about 4 inches deep across the entire Central Valley. Every year we flood that, light it on fire, and burn it. 8.6 billion tons of coal, that's enough to cover all of West Virginia, about 4 inches deep in coal. Think about that. And we burn enough natural gas each year to cover the entire US with a layer of natural gas 1 foot deep. Now, in addition, we also, over 12 years, from 2000 to 2012, we burned about 370 million acres of forests. That's an area equivalent to Texas, California, and Arizona combined. A little bit of good news, the net rate of forest loss between 2000 and 2015 was half that we experienced in the 1990s, so progress in that area. But still, I want to try to give you some sort of spatial sense as to how much fossil fuel gets burned each year. And then this is the distribution of greenhouse gas emissions by sector globally. So similar to the US, but a little bit different. Another thing that I think we take for granted is the size of our atmosphere, right? When we stand on the surface of the planet and look up, it feels infinite, right? You can see all the way to the stars, the moon. We forget that the atmosphere itself is really this thin, narrow blanket that shields the Earth, right? It's just about the troposphere itself, where most of our atmosphere is contained. It's only about 11 miles deep, and all the way up to the stratosphere is just 30 miles. So when you see it from space, you realize just how thin our atmosphere is. And when we burn most of our fossil fuels, we don't see those emissions, right? They're going through catalytic converters. They're going through different filters to take out the particulate matter and take out the aerosols, right? This is a shot from the Deepwater Horizon oil spill. And there we're looking at that was about 5 million barrels, right? Keep in mind we're burning close to 33 billion barrels. What we're looking at is probably a couple thousand barrels, maybe tens of thousands of barrels that are on fire. And you can see the plumes that you generate. So when you are able to see the particulate matter, you get a sense as to how much carbon dioxide is being emitted across the planet and how quickly we actually can fill up our atmosphere and change the composition of greenhouse gases in the atmosphere. The total heat being trapped by these gases is equivalent to detonating about 4 nuclear bombs the size of the Hiroshima bomb per second all year long. So that's how much extra energy we're adding to the Earth system by burning these fossil fuels and through the loss of carbon from deforestation. Okay? So we've been doing this for a long time. Since the 1950s, we've been measuring this at a network of stations around the world, starting with Mauna Loa. This is the famous Keeling curve. I'm guessing Dr. Cordero showed this to you. So we've seen, since the pre-industrial period, about a 40% increase in greenhouse gases. The oceans helped us out. The oceans have absorbed about roughly 30% of the total emissions. This has reduced the accumulation of greenhouse gases in the atmosphere, but of course that's also contributed to ocean acidification. These concentrations are unprecedented over the last 800,000 years. So ice ages, all the natural variability and fluctuations, we have not seen concentrations on these levels, and we're headed for even more. So you are roughly here right now. We crossed the atmospheric threshold of 400 parts per million CO2 as a daily average for the first time in May 2013. We got up to close to 407 parts per million globally earlier this year in about April. As of June, we were at about 406 parts per million. So there is that annual cycle where we increase and decrease depending on whether you're in the northern or southern hemisphere. We are now growing or increasing our atmospheric concentrations of CO2 by about 3 parts per million, 2.8, 2.9 parts per million per year. So we're on track to hit 415 parts per million by 2020. And unfortunately, that puts us right on this high emissions scenario. So this is our business as usual scenario. When we talk about uncertainty and climate change, the biggest driver is what people are going to do. Right? That's the thing that's hardest to model and hardest to capture accurately. So to do that, the climate modeling community develops these scenarios, which we call representative concentration pathways, which entail assumptions about how human society is going to manage energy and manage natural forests going into the future. And we develop these scenarios. Our best achievable or our best case put us at about 420 parts per million. Again, we're on track to hit that by 2020. It's probably off the table. At the moment, we're tracking a scenario that's going to put us closer to about 900 parts per million of CO2 by the year 2100. So that's our business as usual scenario, or our high emissions scenario. I did want to show you a quick video just to kind of put this in perspective as to how stable this is over time. Let me jump ahead to save time here. So this is this curve. This is another representation of the curve I just showed you. This is sort of going back now through looking at CO2 concentrations from ice cores, bubbles from ice cores. So this is going back about 1,000 years here. And this is from the Law Dome ice core, and then there's a whole series of ice cores that allow us to go further and further back, all the way to 800,000 years. So I just want you to get some idea as to where we are now. Given the historic variability, you can see what variability typically occurs between glacial and interglacial periods, going back 50,000 years, 60,000 years, 70,000 years, we're getting up to 100,000 years. Here we're going to switch over. This is the Vostok ice core. We're going to switch to the Epica Dome C ice core in just a minute. So you can start to get some sense as to how stable things have been overall and how unique these atmospheric conditions are at present. So this is going back about 800,000 years total. So hoping to try to give you some additional sense of the scale of these things. So here we are today. This is circa 2008. This is this historic record we just showed. This is our best case scenario, sort of what we consider our best achievable case right now, around 500, 550 parts per million by the end of this century. This is going all the way up to 900, business as usual, assuming no coordinated global action is taken. The other really important point for you to consider as engineers is we don't just stop emissions at 2100, right? We're still here on the planet, hopefully. We still have a strong, growing economy. There will be continued emissions from agriculture, from land use change, and from presumably some continuing use of fossil fuels. Even if we did stop those emissions, right, this is an experiment where they sort of simulated emissions from 1900 to 2100 and then turned them off. They persist in the atmosphere for centuries. Right? This is the residence time of the CO2 that's emitted out another 300 years beyond 2100, out to about 2400, and this is the predicted temperature change as global temperature average as a function of those emissions. So the decisions we make today, whether we develop solutions or don't, will affect us for centuries, right? So not only our kids and grandkids, but their kids and their grandkids. So really important. In total, about 15 to 40% of the emitted carbon remains in the atmosphere for the next 1,000 years, right? So let me turn to impacts now. Why does it matter to engineers? What are the types of problems that you might be faced with solving in your careers? Right? So again, engineering I think of as the discipline of solving problems that affect people. So when you look at the National Climate Assessment, it is your guidebook for job security. Right? These are problems that are likely to require engineering solutions for a long time. Here's the headline from the last IPCC report. This is the consensus statement from the global science community. Warming of the climate system is unequivocal. Since the 1950s, many of the observed changes are unprecedented over decades to millennia. The atmosphere and ocean have warmed. the amounts of snow and ice have diminished, sea level has risen, and the concentrations of greenhouse gases have increased. I'm often asked about uncertainty. How certain are we in the models? I touched on sort of the differences in greenhouse gas emission scenarios. The climate science community continues to work and improve the models. There's questions about what's going to happen to extreme events, how will precipitation change, how quickly will ice melt at the poles, what are the feedback loops yet that we haven't discovered. So those are all things that the community is actively working on and trying to understand. But at the end of the day, I can't think of another issue where there is consensus among 195, hopefully still 195 countries, the CEOs of British Petroleum and Royal Dutch Shell, the Pope, and the science community that urgent and immediate action is needed, right? So there is a strong consensus. Whatever the US government does over the next few years, the global community will be moving forward on changing the ways that we manage and use produce, manage, and use energy, and we will see solutions to climate change developing globally. So it's important, I think, for engineering students to follow these developments, be aware of them, and think about how they might influence your choices as you proceed with your career. So some of the key impacts. The most directly observable one, other than the changes in greenhouse gas concentrations in the atmosphere, global temperature, right? And this is why we call it global warming, of course. These are the observed changes in surface temperature from 1901 to 2012, globally, well, about a degree total on average. That's similar to what we see in the US, about 1 degree Celsius, 1.8 degrees Fahrenheit across most of the US. Higher warming there, especially at our higher latitudes in the northern hemisphere, but also some additional warming there in the southern hemisphere. I think Dr. Cordero touched on this. I just want to emphasize this point. If we don't account for the greenhouse gas emissions, we can't reproduce these with the physically based general circulation models that we also refer to as global climate models. So when you run the models without the increase in greenhouse gas concentrations, this is the projection you get. When you run them with the forcing from greenhouse gas emissions, we are able to reproduce the observed global temperature patterns over the last roughly 100 years, right? So without accounting for the greenhouse gases, we cannot explain the observed warming. I think Dr. Cordero may have shown this, but again, this is showing the net contribution to temperature change from fluctuations in total solar radiation, emissions from volcanoes, and then human-associated emissions. So again, that human-caused driver really explains most of the observed changes in temperature. Another thing to think about as you're developing models as part of your career, as many engineers do, is how good are they, right? You want to test your predictions. And a good way to do that is to run models over a historic period or make a forecast and then compare it to the observations, right? So when I was a student sitting in an auditorium, not unlike this one, there was a couple things we were learning about. Global temperatures will continue to rise, polar ice caps will melt. At the time, those things were not happening, okay? When I started studying climate science and climate change and Earth systems, we were, I hate to admit it, right about here, right? In the 1990s. Since then, the last 3 decades have all been warmer than the previous decade. 16 of the last 17 years have been among the warmest on record, right? So accelerating warming over the last few decades. And you can begin to see the accelerating increase in global temperature and warming. The other prediction was that polar ice caps will melt. And here's our trend here from 1978 to 2015. This is the length of the satellite data record that we have for these observations, as well as coupled with some ground-based measurements. So that's the change in Arctic sea ice. So overall, models definitely capturing some of these major trends, things that without models we would not have been able to anticipate or predict. Another thing I noticed that we're not very good at as people is detecting trends around us, right? Things that are trends. If we look at these graphs, right, it's obvious what the trends are, right? Think of it not as anything to do with climate. Think of it as a stock. If an advisor had told you to buy Apple in the 90s and you saw this type of pattern, you'd say, hey, that guy was really prescient, right? Really insightful. If they told you to sell pets.com and then you saw a trend like that, you would say, oh, yeah. They understood it. They knew what was coming, right? So when we think about these trends and we graph them, it's much easier to see the patterns than it is, say, just observing weather variability, day-to-day variability in what surrounds us each day. We're not so good physically at picking out those trends. We notice the extreme events, but until we start to plot and graph the data, it can be much harder to detect the trends in any long-term conditions. Another animation of Arctic sea ice, just sort of showing you what this has looked like. Again, there's natural variability. There's interannual variability in minimum and maximums of sea ice extent. But when we look at the long-term trend here over the last 35, 36 years, really clear trends. And these are actually happening a little faster than we would have thought in the 1990s. So this acceleration of sea ice melt is definitely one of the things that's concerning and may represent a tipping point. Okay. And then to the point about stability. We talked about CO2 concentrations. To the best of our ability to reconstruct temperature going back through human history to about 200 AD. Again, very stable temperature patterns overall. And when we look at the 1 degree Celsius, 1.8 degree Fahrenheit increase in global temperatures, it's something that is unprecedented in human history. And again, we are about here. And when we look at our best achievable scenario, our best case scenario that we use in the IPCC reports and the National Climate Assessment, again, this would have us just stabilizing at about 420 parts per million CO2, and we're already at 407. The target now is to try to stay below about 2 degrees Celsius, which would put us in this range here. We call this RCP 4.5. And our worst case is up here, about RCP 8.5. Anybody know what those numbers stand for, by the way? And what the RCP numbers? How many of you know what the RCP numbers? Okay, I'll take a minute and explain that then. We measure the effect of greenhouse gas concentrations on the atmosphere in their radiative forcing in watts per meter squared. Okay? So these numbers are the additional energy that's trapped, additional solar energy that's trapped in the atmosphere measured in watts per meter squared. So this is akin to 8.5 is 8.5 watts per meter squared of additional radiative forcing globally. That's like putting out 8.5 Christmas tree lights on every square meter of the Earth's surface forever, for the foreseeable future, right? That's how much extra energy is being trapped by the atmosphere as a function of the greenhouse gas concentrations. I'm going to come back and touch on this in a little bit. Sometimes it's hard to think about, all right, 5 degrees Celsius, 9 degrees Fahrenheit in winter, that might be kind of nice, or if on a cool fall evening, you think, it would be nice if we had a balmy day here. But I want to show you what these temperature projections look like when you impose them at high spatial resolution. The general circulation models that we run, the global climate models that are used as the basis for all of our climate reports, they run at between 1 and 2 degrees currently, and that's kind of what it looks like. Engineers, city planners, you have to work at local scales, right? So you need information that's specific to your city, your community, your county. To do that, the science community has been trying to combine, or has been combining, these coarse resolution global data with high resolution historical data to improve local scale information. So a few years ago, we produced the first really local scale data sets for the US. These are at 800 meters, or about half a mile per pixel. So really one scenario for every city, town, and county in the country. There are 34 different models. We looked at all 4 different possible representative concentration pathways. It was about 17 terabytes of data. I'll come back to this in about 10 or 15 minutes, but I want to show you what these look like. So this is the historic data. This is 1950. This is the typical maximum daily temperature in July. So this is the average for the July. This isn't the heat waves. This is just your typical high temperature for July 1950. I want you to, 105 here is the upper end of this scale. I want you to remember that number. I'll come back and explain why it's important in a minute. That's about 40 degrees Celsius. Notice that the only place that really typically experiences temperatures like that historically is sort of the desert Southwest, the area around Phoenix, Tucson, Death Valley. Let's see how these patterns change. So this is 1960. 1970, 1980, 1990, you start to see the warming that we saw in those graphs earlier kick in here. 1990, 2000, 2010. Okay? Now we move on to the projections. So this is what the climate models tell us is likely to happen under our business as usual scenario, under that RCP 8.5 high emission scenario. 2020, 2030, 2040, 2050, 2060, 2070, 2080, 2090, 2100, right? So Without action taken, that's where we're headed, right? That's our business as usual scenario. What do you notice? Right? All of a sudden, we're all living in Phoenix, right? And what else do you notice? Where are our big agricultural areas? Right? Central Valley, right? Great Plains, Central U.S., right? So all of our big agricultural areas start to have temperatures above 105, 40 degrees C on a typical July day, August day. Again, never mind heat waves, never mind extreme events. This is what you'd expect for averages, okay? We don't have to go there either. This is what it looks like if we well, this is now kind of hard to achieve, but if we were able to stabilize atmospheric CO2 around current levels, around 420 parts per million, this is how the temperatures would look like in July. So really big contrast, right? So that's why when you think about 5 to 9 degrees Fahrenheit, this is what we're talking about, and this is why the science community is concerned. Okay, these are the comparisons there. All right, so why 40 degrees Celsius? Why does that matter? Okay, so this is a graph, a chart of temperature effects on crop production. These are our major staple commodity crops here: corn, sorghum, beans, cotton, peanut, rice, soybean, tomato. This is the failure temperature for reproductive yield. Are any of these numbers above 40 degrees Celsius, 105 degrees Fahrenheit? No, right? So that's not good news. When we look at the projected change in crop yields in 2050 from the World Bank, this is what we see. And notice, again, many of those areas that start to correspond with higher and higher average summer temperatures are associated with the predicted yield declines. This is an area of active study for the climate, for the climate science and agricultural community. For those of you interested in bioengineering and biotechnology, temperature-resistant crop varieties, and improving water use efficiency in crops, guaranteed job security, right? Anyway, this is concerning. Precipitation. The models have a harder time with precipitation trends. A lot more interannual variability, a lot more spatial variability. This is one of the key areas of research in climate science and in our downscaling work, our ability to produce accurate local scale information on climate change. These are the observed precipitation trends over basically the last century, 1901 to 2006. You can see some long-term trends towards dryness in the southern half of California, southwestern U.S., some of the overall, maybe a slight increase in the northeastern U.S., but not strong trends relative to the observed interannual variability. But keep in mind, while we're thinking about agriculture, almost 60% of our irrigation withdrawals come from surface water, right? So if we nudge this even a little bit, that's going to affect our ability to supply agriculture with water. And we've gotten a taste of that, and I'll touch on that in a few slides. Similarly, increases aren't always good either, right? Increases in extreme precipitation events, as we've seen over the last couple of months, can create enormous challenges, especially for large urban cities, but also for rural populations. This is where we're headed. These are the projections. These are this is the old nomenclature. B1 is our lower emissions scenario. A2 is our higher emissions scenario. California in general, we are roughly about here. California in all of these scenarios tends to sit kind of right on the border between areas that are likely to get a little bit drier and areas that may get a little bit wetter. So a lot of uncertainty about what's going to happen overall for average precipitation in California. But as we've seen in California, average precipitation doesn't matter, right? If we take 2015 and 2017, about average year, but huge impacts for agriculture, huge impacts on water supplies, huge impacts on communities that were affected by rapid declines in groundwater in the Central Valley, and then flooding and impacts to reservoirs due to snowmageddon over this last year. When we look at the predicted increases in extreme events, this is the observed increase in extreme events from 1958 to 2012. Not much change for the southwestern U.S. where we are, but big observed increases in the frequency of these heavy extreme events in the northeastern U.S. as well as the southeast and the central U.S. When we look towards the future, this is what we get under our lower emissions scenario and then under our higher emission scenario. So under that higher emission scenario, we expect an increase in these really heavy rainfall events, the return interval of the 20-year extreme precipitation across the board in the U.S. So that's a new finding from the USGCRP Climate Science Special Report that was just published a couple months ago. It's still in draft form, but the text is pretty much finalized. For California, and if you're thinking about engineers, and especially for those of you who are civil engineers, what we really care about is not just the precipitation, but whether it falls as rain or snow. And also when it melts and runs off the mountains. We are so dependent on using our winter snowpack as essentially this massive free natural reservoir. What we've observed from 1948 to 2002 is this increase in melting. So that snowpack on average is melting earlier and earlier each year. You can see in a number of locations, it's anywhere between 10 to 20 days earlier over the last 50 years. When we look towards the future, that gets even worse. All right? So our projected snow water equivalent stored in that winter snowpack under our business as usual scenario is about 60, well, by the time we get out to the middle of this century, about a reduction of about a third to 66%, and by the end of this century, a reduction of more than half, right? So that drives changes in the timing of runoff, soil moisture, and vegetation water stress. So all that water that used to gradually melt from the snowpack throughout the summer isn't available for our high-altitude montane ecosystems anymore. It's going to change evapotranspiration patterns, the timing of plant growth, and that has big impacts on the demand for water storage and the availability of water storage, as well as for fire return intervals, fire risk, aquatic ecosystems, and on and on and on, right? So for those of you thinking about civil engineering, really important to pay attention to what's going to happen to our water supply infrastructure and how climate change affects the timing of runoff and the snowpack stored there in the Sierra during the winter. California ag, also highly vulnerable to climate change. A couple years ago, net returns of more than $40 billion a year in cash farm receipts, about 77,500 individual farms. We're a huge supplier of domestic and international, huge supplier both domestically and internationally for specialty crops. We produce about half of all U.S. grown fruits, nuts, and vegetables. So California is a really important part of the U.S. food supply system and our infrastructure for producing and distributing food. And we grow about 400 different crops in the state. So, and these are primarily for the commodities, not as much for the specialty crops. We talked about some of the global patterns earlier. I wanted to show you what the predictions are for California. Alfalfa looks okay, but when we look at corn, tomato, rice, wheat, cotton, sunflower, again, that same pattern that we saw in the global data being echoed locally for California with predicted declines over the next 50 to 100 years in the average annual yields for those crops. We're also starting to see a few things that are kind of concerning. And the satellite, we can't directly attribute these to climate change itself, but it is a signal that we need to monitor. In 2012, we observed reductions in peak growth in most of the major ag regions in the world. So across the central US, Argentina, Brazil, the Ukraine, even in India, which originally we thought was all right. Once we looked at the actual precipitation anomalies, we saw that the clouds that we saw in the satellite data weren't actually producing rain. Heavy cloud, no rain. So even India was experiencing significant droughts in 2012. Those combined concurrent drought events and reductions in crop production resulted in another spike in crop prices in 2012. And this was the first time we'd seen two large spikes in commodity prices globally within the span of a decade. So another concerning signal. Just to see what that looked like in California, this is 2015. This is the these are maps of crop versus fallow land in the Central Valley. We saw an increase of about 500,000 acres. This is using satellite data. We were able to detect an increase of about 500,000 acres of land that was fallow during the drought relative to normal years. Wildfire risk, I mentioned this earlier. These are the projections for increase in wildfire risk under our business as usual scenario. Here on the right, so we can see throughout the Sierra and along the Coast Range, even here in the Bay Area and around Monterey Bay, it projected increases of anywhere between 200 to 400% in fire return, or the fire risk, decreases in the fire return interval, and then potential increases in fire severity. Here again, we have our higher emission scenario, A2, our lower emission scenario, and we can start to see the average increase in the risk ratio of about 4 to 500% increase in risk relative to 1981 to 1990. You're moving out towards the future. So for those of you also thinking about material science, the need for new building materials, I think Dr. Cordero touched on this, different ways to design homes, roofs, building materials to be more fire resistant, another important topic. Aerosols and aerosol management, ways to design cities to be safe and effective for folks that have susceptibility to aerosols and asthma, another important consideration. So when we see these fire events, you get a sense as to how destructive they are. Increases in electricity demand. Did Dr. Cordero touch on this last week? Yes? Yes, okay. I'll skip this one then. Another one, sea level rise. Did he touch on this one? Have you guys seen this figure? This is a good one for us, right? So sea level rise gets us two ways. One, just a gradual increase. Second, it exacerbates storm surge. So when you look at the combined effects of sea level rise and storm surge, this is an impact of a 1 meter rise in sea level for the SF Bay Area. These are all the areas that would be affected. We've already seen roughly about 20 centimeters of increase over the little more than the last 100 years in sea level. So this is where we are today. And the scenarios put us anywhere between 1 to 4 feet. The new National Climate Assessment, our upper limit used to be about 6 feet. The new scenarios for the National Climate Assessment now include a scenario of up to 8 feet by 2100, in part in response to the accelerated increase in reduction in Arctic sea ice. So this is, for us here locally, this is a big one, right? So how we start to design infrastructure to be resistant to increases in sea level and accelerate and increases in storm surge is really important. This is most of our economy here. So Google, Facebook, a lot of the tech companies have offices here. So ensuring that we can protect and sustain that infrastructure is really important to our local economy, of course. I don't want to leave you with only bad news. So I want to say a few words about reasons for optimism and hope. Not least among these reasons is all of you in this room. Again, having bright, talented, energetic folks interested in developing solutions to problems and aware of the potential impacts of climate change, I think is really valuable. I hope you look at this as an opportunity and not just a reason to be depressed. So I really like what John Holdren had to say, which is that we basically have 3 choices when we think about climate change. We have mitigation, right, reducing greenhouse gas emissions, thinking about better ways to produce and use energy. We have adaptation, which is what engineers, a big part of what engineers and civil engineers will help us do, and suffering. And we're going to do some of each, and the only question is what the mix is going to be. Obviously, the more mitigation we do, the less adaptation will be required and the less suffering there will be. Have you guys seen this figure before? Anybody? Who's seen this figure before? Anyone? This is the good news. I think this is the best news. This is a study that was done by the McKinsey consultant company about the cost of reducing greenhouse gas emissions. Everything here on the left has a net economic benefit, and then everything on the right would have some cost given current technologies. New technologies might reduce those costs. So this is the net benefit. And the good news is that there's a whole host of things that we can do today and are doing in many places that not only reduce greenhouse gas emissions, but have a net economic benefit, a cost savings or an increase in economic activity. So there's things like switching to LEDs, improving appliance efficiency, hybrid cars, changing the way we till and manage land, changing the way we manage rice production, increasing the use of small hydropower systems, changing the way we till and manage residue on croplands, a whole host of things that are all solutions. And then there's a whole other set of solutions that have relatively low cost. Many among these relate to energy efficiency. I think Dr. Cordero talked about this a fair bit. One thing I want to emphasize about this point, this is a curve of residential electricity use per capita from 1960 to 2009. Here's California, right? Where due to some really smart policy, effective policy, good building codes, good practices that encourages use of efficient appliances and efficient building materials, we've pretty much stabilized. Here's the rest of the country. How many of you feel like you're short on electrons? Deprived of electrons? Can't charge your phone? No one, right? So that's the good news, right? California serves as a model for what other states and much of the rest of the country can do to reduce greenhouse gas emissions without depriving anyone, right? So other good news, we see the rapid decline in solar price trends. For those of you interested in material science, fantastic field to get into. So it's now at the point where the cost without subsidies is starting to approach the cost with subsidies. And then, of course, we're seeing this dramatic increase in acceleration in the deployment of solar, especially here in California. So a large increase in our utility and local scale photovoltaic capacity. One more reason for optimism. Here are two breakdowns of total production of electricity by source. On the left is a country which is 33% renewable, 21% nuclear, so more than half non-fossil fuels. On the right is a country that is 9% renewable, 8% nuclear. Anyone want to guess what the country on the left is? Come on, give me. France, Sweden, Netherlands, all good guesses. How about on the right? What's the country on the right? US. Okay, that's an easy one. All right, so the one on the right is US. You got that one. Spain. Spain is on the left. It's one thing to get beat by Spain in World Cup soccer. Totally fine with that. And it's another thing to get beat, in who makes the best paella. Okay, fine, we'll give Spain that one. But innovation and energy production, no. No, we can't lose in that area, right? So I think there are examples from Europe and how we do this effectively without negatively impacting the economy or the experience of any of us on a day-to-day basis. Okay, so again, good news. And so really we have this question about kind of which future do we want to pursue, which future do we want to live in? And the really good news is that it's up to each of you, right? When we look at a lot of the solutions, the new technologies, engineers and scientists have a role in understanding, developing, building, and testing, and deploying and marketing these technologies. So I think really good news about the types of options we have available to us and the growth in technologies that are both energy efficient but also fun to use, fun and effective to use. There's a challenge, though, for engineers, right? And we've seen some really nice examples just in the last year. So on the left, we have the Oroville Dam. On the right, we have Houston after Hurricane Harvey. Here's the challenge. When you're building things, especially on the civil engineering side, the standard practice for a long time has been to look at historical averages to guide your design criteria, right? And we can't really do that anymore, right? Houston has had 3 500-year events in the last 3 years. We had this, we had record-setting drought followed by record-setting snowpack. There's snowmageddon. So we're swinging back and forth from one extreme to the other. That's really hard on engineers who are tasked to thinking about not only do I have cost constraints, but how do I design a building or a structure or a canal or a levee or a dam to be effective under average conditions, but also to hold up under extreme events that we may never have seen before. Good news is that the climate science community has heard that. We're working on trying to produce better and better data sets, both for the National Climate Assessment and the US Climate Explorer, to make it easier for folks to try to get a handle on what the future may hold. Our own work at NASA Ames uses the NASA Earth Exchange, which is a collaboration between the Earth Science Division and the supercomputing group there, this supercomputing division at NASA Ames. And we've taken a lot of the global satellite data sets, Earth observation data sets, outputs from global climate models, brought them all together on the supercomputing platform to make it easier for us to accelerate science, to understand changes in the Earth system, and develop data products that are intended to help assist with climate resilience planning and guide decision making. So this is a capability at Ames. If folks are interested in high-performance computing, interested in earth science, interested in engineering, please come talk to me and let me know. I touched on this earlier. So the way we translated the figure on the left from the figure to the figure on the right is we used 56 years of gridded historical weather data to capture the spatial and temporal distributions of temperature and precipitation at spatial scales that are much, much finer than we can do in the GCMs. We then use the supercomputers to calculate a set of correction factors for temperature and precipitation that allowed us to correct for any local scale biases in the global models, and then disaggregate each of those 1 kilometer cells into the 1 degree cells, 100 kilometers by 100 kilometers, into these 1 kilometer cells, roughly half a mile by half a mile. Again, we did 33 of these global models, 4 representative concentration pathways, and then this data is available in multiple different ways, and I'll touch on a few ways to get access to it. But these give you local scale monthly scenarios for understanding potential changes in temperature and precipitation. 2 other data sets that are also, one, the bias-corrected constructed analogs was developed by the Bureau of Rec, also on the supercomputers at NASA Ames. These give you daily temperature and precipitation projections at a spatial resolution of about 12.5 kilometers by 12.5 kilometers, or 7.8 miles by 7.8 miles. So for engineering, monthly averages are great. They kind of give you sort of the broad picture, but what you really want is what's going to happen with daily conditions, right? That helps us understand the extremes. Recently released, just 2 years ago, the locally constructed analogs. These are similar. These also use a bias correction and constructed analog approach. These reduce the spatial resolution to about 6.25 kilometers, 1/16th degree, and they provide significantly improved projections for precipitation at local scale. That's the main advance. These the local data sets are not yet available on the Climate Explorer, but they will be released here over the next month or two. Knock on wood. So in the past, the climate science community has produced archives of data that were largely held on high-performance computing resources or stored by scientists locally. And that is changing. The rise of cloud computing, the availability of large data storage and high-performance computing, I think is really changing the paradigm and the way we think about not only producing these data sets, but how we distribute them. So right now, data sets that we produce at NASA and other data sets that are produced at NOAA and some of the regional climate modeling centers and national and global climate modeling centers are still just archived on resources like the NASA Center for Climate Simulation, these big, massive scientific data archives. Also put on web-based data distribution systems like the Lawrence Livermore National Labs Green Data Oasis. That's a great resource if you want to download the full data set and do simulations or do model analysis yourself. Great place to go and get that data. Also now making the data available on the Amazon cloud, so it's there and accessible if you want to write scripts or run models and directly access that data without downloading even a single gigabyte, and also through Google Earth Engine. So additional cloud-based computing interfaces that are designed to make it much, much easier for folks to access and work with data. Now, the step that's occurred really just in the last 4 or 5 years is the distribution of these data sets via publicly accessible web-based systems. I'm going to just touch on two, the Climate Explorer for the U.S. Climate Resilience Toolkit and CalAdapt. Strongly encourage you to go and take a look at these sites. I'll make sure that the links to them are available on the Green Talks website. But these are tools that have been developed and will continue to be improved to increase access for folks like yourself to these data sets. Here's the Climate Explorer. If you have a laptop or tablet, go ahead and pull it up. You can just Google Climate Explorer. It should come up. It's version 2. The full link is down here as well. Toolkit.climate.gov, Climate Explorer-2. If you need a minute to take a breath and focus here on this part. If you skip or zoned out for part of my talk, this is the part that I really want you to walk away understanding and knowing how to use. Here are the results for San Jose, California. So we have now climate scenarios for every county in the US. So this is for Santa Clara County and San Jose, where we are here. And these are the temperature, mean daily maximum temperature projections for Santa Clara. On the left, we have in the gray area here, this is what we call the hindcast, the model hindcast or historical experiment. So we run the models from 1950 to 2005, and then we can compare them. These are the bias-corrected downscaled models. We can compare them against the observed climate. So these dark gray bars are the observed temperature conditions from 1950 to about 2010, 2011. And we can see that the models as an ensemble are doing very well at capturing the interannual variability for San Jose, right? Increasing our confidence. We can also track how they do as we move into the future to see are the model projections, do they encompass the observed climate as we move into 2020, 2025. We have two different scenarios here. We have the lower emission scenarios. This is RCP 4.5. This is considered, that's that roughly 2.5, 3 degrees of warming Celsius. This is our best case condition at present. And the red lines here are our business as usual scenario. This is that 3 to 5 degrees Celsius of warming, 5 to 9 degrees, maybe even 10 degrees Fahrenheit warming. The dark lines here are the median. So this is the statistical summary of all of the climate models that were run. And then this gives you the distribution, some measure of the uncertainty or the range of future conditions you might have to account for in designing infrastructure or building building new products. So you can download these as graphs. You can download the data for these graphs directly. In addition to the mean daily maximum temperature, there's annual, monthly, and seasonal summaries, mean daily temperature, minimum temperature projections, information on those, some information on extremes, days above 95 degrees, days with minimum temperatures below freezing. You can also see maps here. You can you can slide through time from 1950 to 2090 and see how spatial patterns in temperature have changed over the last 50 years, or not changed, as the case may be, and how they're anticipated to change in the future, similar to the types of animations I showed you a few minutes ago. You can also look at extreme events. So this is the graph for Santa Clara County, the increase in days with maximum temperature above 95. Under our best case scenario, not too bad. So again, here's our historical conditions. This is our best case scenario. Under our business as usual, it's grim, right? We had that heat wave a few weeks ago. You know how uncomfortable it can get. Worst case, we're looking at potentially 2-3 months like that each year. The ensemble is somewhere around 30 days per year. Ensemble median is somewhere around 30 days of temperatures above 95 degrees for our local area. So important to think about as you're considering maybe building designs, HVAC systems, how you would scale some of the HVAC systems for large buildings, how you might think about designing cities to reduce urban heat island effects. Again, looking at maps, you can see this data spatially through the Climate Explorer, see the patterns, see the effect of the coastal cooling, ocean cooling, coastal fog on our coastal systems, projections in changes in days below freezing, as you would expect, rapid declines. Actually, and what's interesting here is we see declines in the days with minimum temperature below 32 in both scenarios. So this is something that seems to be consistent both under our high and low emission scenario for Santa Clara County. Precipitation. Here we can see what I was talking about earlier, a lot of variability, much more variability around the model ensemble median than for temperature. But overall, this is what's important. When we look at the historic projections, they seem to do a reasonable job of capturing the observed interannual variability. When we look towards the future, overall not a strong trend, but we do start to see some increase here in the extreme events. So at the upper end of the range from all of the models, evidence that we might expect increases in extreme events and heavy precipitation events. Also look at days of precipitation above 1 inch. Another way to view this data or try to get a sense. You can also display not only the actual values, but you can toggle back and forth if you want to look at actual or anomalies. Here's a map of the percent change in precipitation for January for California and the southwestern US. One of the last features I wanted to mention for the Climate Explorer is you can also go and you can use it as a quick and easy way to access information from weather stations. So you can actually go and check and see how's the year-to-date precipitation, how is temperature for Santa Clara County, what's happening? Does this appear to be an extreme year? Is it following the average? Where are we at? So here is for precipitation. We can see 2015, that really dry year, followed by 2016, close to average, and 2017, which started off well above average. So ability to get direct access to observations that you can use to compare to long-term averages as well as the climate projections. The other website I want to mention is CalAdapt. You can, again, just Google CalAdapt. I encourage you to take a look at the beta version. It might now be released. I haven't checked. Beta.caladapt.org. In addition to information on temperature and precipitation for California, it also includes some really nice summaries of potential changes in snowpack, potential changes in wildfire conditions. One thing I want to mention about the Climate Explorer is that it's intended in its current form as a starting point. And we're hoping, as long as there continues to be support from it from the federal government, and as long as NASA, NOAA, and the U.S. Bureau of Rec, and EPA, and the Park Service can all continue working together on the toolkit, that we'll be able to add additional variables. So some of the variables and some of the information that's available in CalAdapt will also be available nationally in the future. But especially for snowpack and information on changes in wildfire, CalAdapt is a fantastic resource, and the folks that have worked on it have done a beautiful job. I'll make sure these links are available, just some additional resources, sources of information. Again, if you take away nothing else from this talk, please take a look at the Climate Explorer. Think of it as a resource. If you have ideas for improvement, send them in. There's a Contact Us link there. And also take a look at the National Climate Assessment. If you're an engineer, this is your guidebook of problems that will need to be solved in the future. So with that, happy to answer any questions. Thank you so much for your time and interest, and yeah, really a pleasure to be here today. Thank you.
So do we have any questions? Here's one right here.
At one point you said 34 GCMs, and at another point you said the slide said 33.
Oh, sorry. So there's more than 34 GCMs. At the time we produced this data set, there were 33 GCMs that had completed their data. So we used, I think, 33, and then we finally went back and added a 34th GCM that had monthly data that we could use. For the daily scenarios, there were 21 of the global models that produced daily scenarios that we could use for the downscaling.
Do we have any other questions?
And there's more than that in the full IPCC set of models.
I'm just curious, what's the method used to collect the RCP data?
So the RCP data itself, that's developed by teams of economists. So the RCPs, let me jump back. The RCPs are done based on a combination of observed greenhouse gas concentrations, information on energy usage, and then some assumptions that are put together by economists and social scientists to try to develop realistic scenarios that represent the potential. Let me go back up here. Sorry, let me get that. So these are essentially derived from economic and social models about the potential decisions folks can make. This is the hardest thing, I think, to represent scientifically because it's so hard to anticipate breakthroughs in technology. The important thing is to keep track as to which scenario we are following. There's not much divergence. There's still time to change scenarios. But at the moment, we are tracking this high emission scenario and have been for some time. Does that answer your question? Yeah.
We have one more question.
Do you also have data showing that the Earth's mantle is getting warmer due to increase in temperatures in the Earth?
Data on, so yeah, so we have, so let me see if I can find a figure here. You said about the Earth's mass, or
yeah,
about?
the Earth's core and mantle, is it getting warmer? And if it is, what are the future problems?
Right, so again, from all the analysis that's been, so the Earth's mantle and core haven't changed. One of the things that was that folks asked about was, what about volcanic emissions? Emissions of CO2 and aerosols and things like that. So when you have volcanoes erupt, they do two things. They emit carbon dioxide and methane. It's about, on average, 1% of what humans emit per year. And then they also emit aerosols, right? So they kick up all this dust and all the aerosol emissions. The aerosols actually reflect sunlight. And so the net effect of volcanic emissions is to cool the Earth, right? You think about Mount Pinatubo was this huge eruption that actually resulted in the short-term cooling of the global surface temperature. Once those aerosols settle, then the Earth's temperature, resumed. But the net effect of volcanic emissions is to cool the Earth. So that's actually something that served as a small break on the change in temperature over the last century. Other questions? Yeah. Barbara, there's one more in the front.
Okay. Oh, one more.
When climate scientists are taking a look at these data models, do they take into consideration soil erosion and if those areas are still habitable by humans?
So soil erosion from the global climate models happens at a spatial scale that's much too fine, right? That's a really fine scale process. Part of what we're trying to do with these higher resolution scenarios is allow hydrologists and soil scientists to look at, get accurate, realistic projections of future temperature and precipitation conditions so they can start to model how these main global drivers might influence local scale hydrology, including changes in runoff, increases in extreme events for runoff, which have strong influences on erosion. Other folks are looking at modeling the impacts of increased temperature and reduced precipitation on loss of forest ecosystems, conversion of forest to grasslands, and how that might affect not only soil hydrology, but also loss of soil cover. So that